Our universe has a fundamental speed limit, just like a game's processing power. The very fabric of reality might be made of tiny, indivisible pixies. Some physicists have even found what looks like error-correcting codes in the equations describing fundamental forces. And get this, particles seem to snap into existence only when we observe them, as if the universe doesn't bother rendering things no one is looking at. Number 9. Where is everybody? Maybe they're not in our part of the game. The universe is, by all accounts, staggeringly fast. Our own Milky Way galaxy contains hundreds of billions of stars. Scientists estimate there are trillions of galaxies in the observable universe. Many of these stars likely have planets, and a fraction of those planets could exist in the habitable zone, where conditions might allow for liquid water and potentially life. Given the sheer number of potential cradles for life and the immense age of the universe, about 13.8 billion years, one might expect the cosmos to be teeming with civilizations, some far more advanced than our own. This expectation leads to a famous question posed by physicist Enrico Fermi in 1950. Where is everybody? This is the heart of the Fermi Paradox. If alien life, especially intelligent alien life, is statistically probable, why have we found no verifiable evidence of it? No signals, no megastructures, no probes, nothing definitive. This silence is sometimes called the Great Silence. There are many proposed explanations for the Fermi Paradox. Perhaps life is incredibly rare. Perhaps intelligent life is even rarer or self-destructs before it can explore the stars. Perhaps vast interstellar travel is simply too difficult or not worth the effort for advanced civilizations. Another concept often discussed is the Great Filter, a hypothetical barrier that is extremely difficult for life to overcome. This filter could be behind us, meaning we are exceptionally rare and lucky to have passed it, or ahead of us, meaning most, if not all civilizations, hit a wall and cease to exist. Now consider how this relates to the idea of a simulated reality. In a computer simulation, especially one as complex as an entire universe, resources are not infinite. The creators of a simulation might choose to focus computational power on specific areas or aspects of the simulation that are of interest. If the simulation is designed around humanity or a specific experiment involving Earth, then rendering countless other complex space-faring civilizations across the cosmos might be an unnecessary expenditure. It's observed in video game design that developers often don't populate every corner of a vast game world with highly detailed interactive characters if the player is unlikely to ever encounter them or if it doesn't serve the main narrative. Alternatively, if we are in a simulation, perhaps the programmers have set specific rules or boundaries. We might be in a sandot environment, isolated from other potential simulations or other parts of a larger simulated multiverse. The lack of contact with extraterrestrial intelligence could, from this perspective, be a feature of the simulation's design, not necessarily a reflection of the actual probability of life elsewhere in a base reality. It could also be that interactions with other civilizations are simply not part of the current storyline or experimental parameters for our particular instance of the universe. The Great Silence could, in this context, be an intentional design choice or a limitation of the simulated environment we inhabit. Number 8. Those weird glitches you notice. Maybe they're system bugs. Almost everyone has experienced a moment of déjà vu, that uncanny feeling of having lived through the present situation before, even though you know you haven't. Or perhaps you've heard of the Mandela Effect, a phenomenon where a large group of people share a distinct false memory about a past event. Examples often cited include misremembering Nelson Mandela dying in prison in the 1980s or the spelling of the Berenstain Bears. children's books as Berenstain. While psychologists offer explanations for these phenomena based on memory fallibility, confabulation, and suggestibility, the experiences themselves are widespread and often quite vivid for those who encounter them. Consider other small, inexplicable oddities. A misplaced object that reappears in an obvious spot you're certain you checked multiple times, a fleeting shadow in your peripheral vision that vanishes when you turn to look, or a moment of extreme coincidence that feels statistically improbable. Most of the time, these are dismissed as tricks of the mind, fatigue, or simply the random nature of life. In the world of computing and software development, bugs are errors or flaws in a program that cause it to produce an incorrect or unexpected result, or to behave in unintended ways. Glitches are often temporary faults. No matter how carefully a program is written, complex software can, and often does, contain bugs. Video games, for instance, are notorious for them. Characters walking through walls, objects floating inexplicably, textures not loading correctly, or game physics behaving erratically. Patches and updates are regularly released to fix these issues. If our reality were a highly advanced simulation, it's conceivable that it too might not be perfect. Even a system of unimaginable complexity could potentially have minor errors in its code or glitches in its operation. From this viewpoint, experiences like déjà vu, shared false memories, or minor, inexplicable physical occurrences could be interpreted not as purely psychological phenomena, but as brief manifestations of the underlying system, momentarily hiccuping or revealing a tiny imperfection in the rendered reality. A misplaced object reappearing could be likened to a data refresh error. A moment of déjà vu could be like a script replaying a fraction of a second too soon, or a corrupted memory cache. The sheer scale and complexity of a universe simulation would make it incredibly difficult to ensure absolute perfection in every detail at all times. What we perceive as minor glitches in the matrix could some ponder be the equivalent of software bugs in an incredibly sophisticated operating system. These wouldn't necessarily be system crashing errors, but small transient anomalies that are quickly corrected or are so minor they go unnoticed by most, or are easily rationalized away by those who do experience them. Number 7. Your brain might be a really good graphics card for consciousness. One of the deepest and most perplexing questions in science and philosophy is the hard problem of consciousness. Coined by philosopher David Chalmers, it asks, why and how do physical processes in the brain give rise to subjective experience, the feeling of redness, the taste of chocolate, the pain of a stubbed toe, the joy of music? This is about qualia, the individual instances of subjective conscious experience. We can understand a lot about the brain's mechanics, how neurons fire, how signals are transmitted, which parts of the brain are active during certain tasks. These are often called the easy problems, though they are still very complex. But how those physical processes translate into the rich inner tapestry of what it feels like to be you remains a profound mystery. Scientists are actively researching the neural correlates of consciousness, trying to pinpoint the brain activity that corresponds to conscious awareness. Yet, a complete theory explaining how matter creates mind is still elusive. We know the brain constructs our reality. What we see, hear, and feel is an interpretation, a model, built by our neural architecture, based on sensory input. Optical illusions, phantom limb sensations, and the effects of psychoactive substances all demonstrate that our perceived reality is generated and can be altered by brain states. Now let's consider artificial intelligence and simulated environments. In video games, non-player characters and NPCs have become increasingly sophisticated. They can exhibit complex behaviors, react to their environment, interact with players, and even appear to have goals and motivations. while current NPCs are driven by algorithm and don't possess genuine consciousness as we understand it. The trend is towards greater realism and complexity. Futurists and AI researchers speculate about the possibility of artificial general intelligence, AGI, and I that could perform any intellectual task a human can. If AGI becomes a reality, the question of whether such an entity could be conscious will become even more pressing. If consciousness is an emergent property of sufficiently complex information, processing as some theories suggest, then it's conceivable that a simulated brain within a powerful enough computational system could in principle generate consciousness. If our universe is a simulation, our consciousness might not be an emergent property of a biological brain in a base reality, but rather an emergent property of a simulated brain process running on a vast computational substrate. Our subjective experiences would be rendered by this system, much like a sophisticated game engine renders a visual world. From this perspective, the physical brain we study might itself be part of the simulation, the in-game hardware that our simulated consciousness experiences as its own. The hard problem might then translate to understanding how the simulation's code or underlying physics engine generates these subjective states within its simulated entities. If it's possible to simulate consciousness, and if civilizations run many such simulations as some arguments propose, then it raises the question of whether our own deeply felt personal consciousness is one of these simulated instances. Number 6. Is everything just data? At the most fundamental level, what is our universe made of? We talk about matter and energy particles like quarks and leptons, and forces like gravity and electromagnetism. But some physicists have proposed an even more fundamental ingredient: information. The late physicist John Archibald Wheeler famously coined the phrase "it from bit," suggesting that all things physical derive their existence from information theoretic underpinnings. This idea posits that the universe, at its core, is not made of stuff but of information, bits of data that, when processed, give rise to the reality we perceive. Think about it. Quantum mechanics, the theory that describes the universe at the smallest scales, is inherently probabilistic and informational. A particle's state is described by a wave function, which essentially encodes information about the probabilities of its properties, like position or momentum, until a measurement is made. The amount of information that can be contained within a given region of space is finite, as suggested by concepts like the Bekenstein bound, which sets an upper limit on the entropy, or information, that can be contained within a finite region of space-time with a finite amount of energy. Black holes are particularly interesting from an information perspective. The Bekenstein-Hawking entropy formula suggests that a black hole's entropy is proportional to the area of its event horizon, not its volume. This led to the development of the holographic principle, which proposes that the description of a volume of space can be thought of as encode on a lower dimensional boundary to that region, like a hologram. If this principle is correct, it means that the three-dimensional reality we experience might be a projection of information stored on a two-dimensional surface at the cosmological horizon. Our universe could be, in a sense, a vast hologram. Computer simulations are, by their very nature, built from information. Code is information. Data structures are information. The rules and algorithms that govern a simulation are information. The state of a simulated world at any given moment is a vast collection of bits. If it from bit is a correct description of our universe, then reality itself operates on principles remarkably similar to those of a computational system. The laws of physics could be seen as the algorithms, and the state of the universe as the data being processed. Physicist James Gates has even found what appeared to be error. Correcting codes, specifically doubly even self-dual linear binary error, correcting block codes embedded within the equations of supersymmetry, a theoretical extension of the standard model of particle physics. Error-correcting codes are used in computing and digital communication to detect and correct errors that occur when data is transmitted or stored. Finding them in the fundamental equations describing reality is, to say the least, unexpected from a purely physicalist viewpoint, but perfectly natural if reality is information being processed, where data integrity would be crucial. This suggests that the fabric of our cosmos might be fundamentally digital, composed of discrete units of information governed by computational rules. Number 5. We're probably not the real ones, statistically speaking. Philosopher Nick Bostrom, from the University of Oxford, presented a thought experiment in 2003 known as the simulation argument. Doesn't directly argue that we are in a simulation, but rather that one of three propositions is almost certainly true. The argument relies on a few basic assumptions: that consciousness can be simulated, or at least that beings who believe they are conscious can be simulated, and that technologically advanced civilizations will likely have immense computational power. The logic unfolds like this. If the first proposition is false, it means a significant number of civilizations do reach a post-human stage. The second proposition is also false. It means a significant number of these post-human civilizations do run ancestor simulations. Because these civilizations would have enormous computing power, they could likely run a vast number of such simulations simultaneously, potentially billions or trillions, each populated by countless simulated conscious beings. If this is the case, then the number of simulated realities would vastly outnumber the one base reality. For every original, non-simulated individual who ever lived in the history of a civilization that reaches the simulation running stage, there would be an astronomical number of simulated individuals in the ancestor simulations that civilization creates. Therefore, if you pick a conscious observer at random from the set of all such observers, real or simulated, the probability that they are one of the simulated ones becomes overwhelmingly high. It's a simple matter of numbers. Many, many simulated minds versus very few original minds. So, unless humanity is incredibly unusual in either failing to reach technological maturity, Proposition 1, or in having no interest in running such simulations once we are able, Proposition 2, then we are forced to consider Proposition 3. This argument doesn't rely on strange physics or glitches in reality. It's a purely logical and probabilistic argument based on assumptions about the future trajectory of technological development and the potential interests of advanced civilizations. If civilizations like ours typically survive and develop the capacity to create convincing simulations of their past, and if they choose to do so, then the sheer number of simulated ancestors would dwarf the number of actual ancestors. Statistically, any given conscious being, like you, would be far more likely to be one of the many simulated ones than one of the rare originals. Number 4. The universe runs on math. Really runs on math. One of the most astonishing things about our universe is how accurately it can be described by mathematics. From the orbits of planets, governed by Newton's laws and Einstein's general relativity, to the behavior of subatomic particles, described by the Standard Model and quantum mechanics, the fundamental workings of reality seem to follow precise mathematical rules and equations. Physicist Eugene Wigner wrote about the unreasonable effectiveness of mathematics in the natural sciences, marveling at how mathematical concepts developed for purely abstract reasons often turn out to be perfectly suited to describe physical phenomena. Consider the constants of nature: the speed of light, cis, the gravitational constant, g, the Planck constant, h, the elementary charge, E, and the fine structure, constant, alpha, among others. These are specific numerical values that appear in our physical equations. What's particularly intriguing is the concept of fine-tuning. Many of these constants and other parameters of the universe, like the strength of the fundamental forces or the initial conditions after the Big Bang, appear to be exquisitely fine-tuned for the existence of complex structures, like stars, planets, and life. If these values were even slightly different, the universe could have been radically different and inhospitable. Perhaps no stars would form, or atoms couldn't exist, or the universe might have collapsed back on itself moments after it began. For example, if the strong nuclear force were just a tiny bit weaker, protons couldn't stick together to form atomic nuclei beyond hydrogen. If it were a little stronger, all hydrogen might have fused into heavier elements early in the universe's history, leaving no fuel for long-lived stars like our Sun. The cosmological constant, which describes the accelerating expansion of the universe, is so small that it's been described as the most precisely tuned constant in all of physics. If it were much larger, the universe would have expanded too rapidly for galaxies to form. This precise mathematical underpinning and fine-tuning of parameters is exactly what one would expect if the universe were a designed system, like a computer simulation. In any simulation, the programmers define the fundamental rules, the physics engine, and set the initial parameters. These parameters can be adjusted and tuned. The laws of physics in a simulation are, quite literally, lines of code or mathematical algorithm. Constants are specific values programmed into the system. The observation that our universe is so deeply mathematical and appears fine-tuned for life has led some to ponder if this is evidence of a designer or programmer. While the anthropic principle offers one explanation, we observe the universe to be this way because if it were different, we wouldn't be here to observe it. The sheer specificity of the mathematical laws and constants remains a source of wonder and speculation. The fact that reality adheres so strictly to mathematical formalisms is strikingly similar to how a simulated world operates according to its programmed logic. If the universe is a simulation, its mathematical nature isn't just unreasonably effective. It's a fundamental characteristic of its design. Number 3. Stuff only yields when we look. The world of quantum mechanics, which governs the realm of atoms and subatomic particles, is famously bizarre and counterintuitive. One of its most mind-bending aspects is the observer effect, or more accurately, the role of measurement. Before a quantum system, like an electron, is measured, its properties, like position or spin, can be in a superposition existing in multiple states simultaneously. It's not that the electron is in one definite place, and we just don't know where. According to standard quantum theory, it genuinely doesn't have a definite position. It's described by a wave function, which represents a cloud of probabilities. When a measurement is made, when we try to look at the electron's position, something remarkable happens. The wave function collapses and the electron snaps into a single definite state. It's as if the act of observation forces reality to make a choice. This was famously illustrated by the double-slit experiment. When particles like electrons are fired one by one at a barrier with two slits, they behave like waves, passing through both slits simultaneously and creating an interference pattern on a screen behind the barrier, even if only one electron is sent at a time. However, if you place a detector at one of the slits to see which slit each electron goes through, the interference pattern vanishes. The electrons start behaving like discrete particles, going through one slit or the other, as if they know they are being watched. This phenomenon, that reality at the quantum level seems to be indefinite until observed or measured, has led to a lot of philosophical debate. Constitutes an observer or a measurement? Does it require a conscious mind, or just any interaction with a macroscopic system? The prevailing view in physics is that consciousness is not required. Any interaction that decoheres the quantum system is sufficient. However, The apparent link between observation and the definiteness of reality has a striking parallel in computer simulations, particularly in video games. To save computational resources, video games often use techniques like culling or lazy rendering. This means the game engine only renders in full detail the parts of the virtual world that are currently in the player's field of view or are relevant to the immediate kilo. Areas that are hidden far away or behind the player might not be rendered at all, or rendered with very low detail until they come into view. The game world, in a sense, only fully exists where and when it is being observed by the player. Why waste processing power on things no one is looking at? If our universe were a simulation, such a lazy rendering approach would be an incredibly efficient way to manage the immense computational load of simulating an entire cosmos. Perhaps particles don't have definite properties until a measurement forces the system to calculate and render a specific outcome. Probabilistic nature of quantum mechanics could be a feature of this resource management system. The universe, in this view, wouldn't bother to compute the exact state of every particle at all times. It would only render the necessary details on demand when an interaction or observation requires it. The observer effect, then, might not be so mysterious after all, but rather an indication of an unpited simulation. Number 2. Reality might be pixelated. When you look at a high-definition digital photograph or a modern video game display, the image appears smooth and continuous. But if you zoom in far enough, you'll discover that it's actually composed of tiny, discrete dots called pixels. Each pixel has a specific color and brightness, and together they create the illusion of a continuous image. The resolution of the screen or image is determined by the number and density of these pixels. There's a smallest fundamental unit to the digital image. Now let's turn to the fabric of space-time itself. According to current physics, there might be a fundamental limit to how small things can get, a sort of pixel size for reality. This is known as the Planck length, approximately 1.6 times 10 raised to the power of 35 meters. It's an incredibly tiny distance, far smaller than an atomic nucleus. Planck length arises from combining fundamental constants, the speed of light, c, the gravitational constant, g, and the Planck constant. Below this scale, our current theories of physics, including general relativity and quantum mechanics, are expected to break down. Space-time itself might not be smooth and continuous at this level, but rather grainy or discrete, like a digital image. Similarly, there's a Planck time, about 5.4 times 10, raised to the power of 44 seconds, which is the time it would take a photon traveling at the speed of light to cross a distance equal to the Planck length. This is considered by some to be the smallest possible unit of time, a sort of tick rate for the universe. Events occurring on times scales shorter than the Planck time are generally considered physically meaningless within our current understanding. The idea that space-time might be quantized, made up of discrete indivisible units, is a feature of some theories of quantum gravity, such as loop quantum gravity. If space-time is indeed pixelated at the Planck scale, it would mean that reality has a finite resolution, much like a digital simulation. In a computer simulation, everything is ultimately discrete. Space is represented by a grid. Time advances in discrete steps, and the properties of simulated objects have finite precision. A continuous universe would require infinite information to describe perfectly, which could pose a problem for any finite computational system trying to simulate. A universe with a fundamental pixel size and a minimum time step, however, would be inherently finite in its information content at any given moment, making it computationally more feasible. If our reality has a fundamental resolution limit, like the Planck length and Planck time, it would be remarkably consistent with the characteristics of a simulated system. It's as if there's a refresh rate and a screen resolution for the cosmos itself. While we can't directly observe anything at the Planck scale with current technology, the theoretical existence of these fundamental limits has led some physicists and philosophers to note the striking resemblance to how digital realities are constructed. The smooth, continuous world we perceive could be an illusion emerging from an underlying discrete, pixelated substrate, much like a movie appears continuous despite being made of individual frames. Number 1. Our universe has a speed cap. One of the most fundamental and well-established principles in physics is that there's an ultimate speed limit in the universe, the speed of light in a vacuum, denoted as c. This speed is approximately 299,792,458 meters per second, or about 186,282 miles per second. According to Einstein's theory of special relativity, nothing with mass can ever reach the speed of light, and nothing at all, not even information, can travel faster than light. As an object with mass approaches the speed of light, its relativistic mass increases, and it would require an infinite amount of energy to accelerate it to c. This universal speed limit has profound implications. It dictates the maximum speed at which any cause can produce an effect, establishing a cosmic speed limit for information transfer. It defines our observable universe. We can only see light from objects whose light has had time to reach us since the beginning of the universe. It's a fundamental constant woven into the very fabric of space-time. Now consider the world of computer simulations, especially complex ones like those used for scientific modeling or large-scale video games. Every computational system has inherent limitations based on its processing power. Computer can only perform a finite number of calculations per second. In a simulation, this processing speed limit directly affects how quickly the simulated environment can update, how much detail can be rendered, and how fast information can propagate within the simulation. If you try to push a simulation beyond its processing capabilities, it might slow down, lag, or even crash. Game developers often have to optimize their code carefully to ensure that the game runs smoothly within the hardware constraints of the target platform. The frame rate of a game is a direct consequence of these processing limits. The existence of a fixed maximum speed limit in our universe, the speed of light, bears a striking resemblance to the processing speed limitations inherent in any computational system. If our universe were a simulation running on some vast unknown computational substrate, that substrate would necessarily have a finite processing capacity. This capacity would naturally impose a maximum speed at which information or interactions could propagate through the simulated environment. The speed of light could be interpreted as this fundamental processing speed of the cosmic computer. Think of it this way. For the simulation to update the state of every particle and field across the universe, calculations need to be performed. The speed of light might represent the maximum rate at which the results of these calculations, the next state of a particle or region of space, can be determined and communicated across the simulated grid. If something tried to move faster than this, it would mean the simulation would need to compute its effects before it had the processing cycles available to do so, which would be impossible. This analogy doesn't prove that the speed of light is a processing limit of a cosmic simulation, but the parallel is compelling. A universal speed limit is a natural feature one might expect to find in a simulated reality, constrained by finite computational resources. The fact that our universe has precisely such a limit enshrined in its most fundamental laws is one of the observations that makes people ponder the nature of reality itself.